Welcome to this lecture series in real analysis. In this lecture, we'll learn about the Archimedean property of the reals. And what we need to know is, of course, what is the meaning of real numbers. So we defined the field of real numbers as an ordered field, which has the least upper bound property. So we have this word ordered field. We discussed this at length. Roughly, a field is supposed to be abstracting the algebraic properties: addition, subtraction, multiplication, and division. Those are the four things you can perform within a field. Ordering gives you a way to compare two elements. And an ordered field is where the ordering and the algebraic properties interact well. So that is the rough meaning of it, and the precise meaning has been discussed earlier. So the real number field is an ordered field, but it does not have the deficiency which the rationals suffer from, meaning every subset of the real numbers has a least upper bound. Sorry, what am I saying? Every subset of real numbers that is bounded above has a least upper bound. Okay, so that is something that that is how we defined the real numbers, an ordered field with the least upper bound property. But we then constructed such an object. So this exists, and we commented that it is unique. The uniqueness was left as an ongoing exercise. As you learn more and more, you can think about how to prove the uniqueness. And there was a certain sense in which it was unique, and that was a pretty natural sense. Okay, so much about the real numbers. And then we need these two words, infimum and supremum. Infimum is just a synonym of the greatest lower bound. So if you have a subset of reals that is bounded below, then the greatest lower bound is also sometimes called the infimum. In fact, many times called the infimum. However, even if your subset is not bounded below, we still use the word infimum for it, but then we declare the infimum to be minus infinity. This symbol, this is just a symbol. And supremum stands for least upper bound. And if you have a subset that is not bounded above, then the supremum is declared to be plus infinity. Okay, so these are roughly the things that we need to be clear about in order to follow today's lecture. Okay, so let's move on. Here are some problems for practice. And now let us get started. So this is the main lemma that we need to establish in order to prove what is called the Archimedean property. We haven't stated the Archimedean property yet, but this is essentially at the heart of it. We will state the Archimedean property next. Okay, so how do we show this? First of all, what does it say? You collect all these numbers. We want to say that the greatest lower bound of this is 0. So first of all, note that this set is bounded below because everything here is a positive number, and hence this is bounded below and hence has a greatest lower bound, meaning it has a real number that serves as a greatest lower bound, and we claim that that number is 0. Pictorially, if you list out the elements of the set, for n equals 1 you get 1, for n equals 2 you get half, for n equals 3 you get 1/3, 4 you get 1/4, and so on. So the numbers here, they come closer and closer to 0, but they never quite become 0. No element here is equal to 0, but they come closer and closer to 0, so to say. We want to show that 0 is the greatest lower bound, and this should be intuitively obvious. You cannot have a positive number that serves as the greatest lower bound. Clearly, 0 is a lower bound. Everything here is greater than 0. And so 0 is a lower bound, but we want to show that it is actually the greatest lower bound. Okay, so let's prove this. And the proof is interesting. It's not clear, it's not entirely straightforward. It has an interesting maneuver. So define as the set whose infimum we want to show is equal to 0. So this is of course a set of real numbers, and we want to show that its infimum is 0. So as we said, this is bounded below. which means that it has a lower bound. Namely, 0 is a lower bound, or any negative number is a lower bound. Okay. So let A be the greatest lower bound. Okay, and we want to show that. Okay, so all we have done is just to restate the thing. Now, here is the thing. Since A is the infimum, we have A will be dominated by everything in the set S by definition of infimum, or rather by definition of a lower bound. And infimum is in particular a lower bound, and hence we have this, which implies this is even more in particular, right? Everything, each number here is an element of the set S, and hence we have this. Okay? This implies twice of A also satisfies this, which implies twice of A is a lower bound. And since it is a lower bound, it is not going to be, or rather it will be dominated by the greatest lower bound, which is A. Right? This was the greatest lower bound, which led us to the conclusion that twice of it is also a lower bound. But since this is the greatest lower bound, it will be dominating every other lower bound. So we have that. And therefore, and since, so here let me write a line. So note that A is at least that much, because 0 is already a lower bound. A is the greatest lower bound, but 0 is already a lower bound, so we have that. The greatest lower bound should dominate every other lower bound, so we have that. And now, since A is a non-negative number with twice of A being dominated by A, this forces you subtract A from both sides, you get that. And now you just combine this with that. This forces that A is 0. And that finishes the proof. It's a nice proof. It's an interesting proof, even though the fact was intuitively obvious. But one has to prove it rigorously, and this is one way to do it. Okay. So now here is the Archimedean property. It says that fix two real numbers x and y such that x is positive. So we have depicted it here. Then there is some natural number n such that n times x dominates y. What does it say? It is saying that, let's say y is somewhere here. It is also positive for the moment. So then it says that if you keep adding x enough number of times, you will jump over y at some point. Again, this is completely intuitively obvious, but it has to be proven rigorously. So that's the Archimedean property, that if you keep working with the constant pace, you will eventually achieve your goal. All right. So let's prove this. So define S as in the previous slide. That's S. Of course, it's a set of real numbers. Then as we saw, that 0 is the infimum. I mean, I'm just restating the previous conclusion. Okay, so this is what we will use. Now, since that is the case, so before I continue, if y were negative, then we were already done. Why is it clear? Because you can just take n equals 1. If y were negative, then of course a positive thing will be greater than a negative thing. So we may assume that y is positive or non-negative. In fact, I can just write less than equal to 0 here. That is also fine. So assume y is positive. Okay, fine. Now, this number is positive, and therefore, since this infimum is 0, we have this must be greater than some element of f. So let me explain this line. We are claiming that there is n such that this happens. Assume that it's false, then we would have this is less than equal to 1 by n for all n, and that would mean that this is a lower bound of the set S, and therefore dominated by the greatest lower bound. The greatest lower bound is 0, and that would mean a positive thing is at most 0, and that would be a contradiction. So that's the reasoning here. Since infimum S is 0, we must have this for some n. The fact that we are using about x by y is that it is a positive entity. So we have this, and now you just rearrange, just do the algebra, and we are done. This is for some n, and we are done. Okay, so that's the proof of the Archimedean property, and it has a corollary. If you have an arbitrary real number, y, then there is some natural number such that this happens. So the proof is a one line or one word kind of argument. Take x equals 1 in the previous lemma. That's it. That proves this. And yeah, this is it. So as usual, like, comment, share, subscribe, and I will see you next time.